All right, so it's some people in the audience here maybe have kept track of the literature more than I have done recently, because there is a lot of work on quantum error correction, and it is a fun area to be working in, also as a theorist, but also as an experimentalist. Just one moment to sort of look back in time. So when I started a PhD, I remember meeting Dan Gottesman at a conference, and he had some ideas about quantum error correction improving on something that Calderberg, Steen, and Shor had done, and I was also very eager to do something, but at that moment I didn't have any great ideas. But so this was around the in the 90s, and that was an era where the theory developed, and it was quite important, of course, to establish that even if we had noisy operations, noisy, measurements, noisy state preparations, we could somehow do reliable computation, and we could do reliable computation, quantum computation, with an overhead which was not exponential, right? Because if it were exponential, we'd be losing any advantage. And the first ideas in this area were put forward by Peter Shor, actually, and then were further developed in threshold theorems by several people: Aronoff, Ben-Or, Laflamme, Knill. And these theorems used a scheme called concatenation that I'll actually mention. You may think that this is just for sort of historical purposes, but I think it gives a perspective that goes beyond code constructions that you may be used to, like the surface code. All right, so essential in these theorems were to how you construct quantum codes, and then how you do computation with them. So you have to also, if you have a code encoding some qubits, you also have to specify how you do the logic in encoded form. And this is not completely trivial if you do this for quantum computation. If we fast forward to what's happening right now, like I said, it's an experimental subject part of the way, or somewhere between experiment and theory, where both parties have to come together, because on the theory side, we need something called decoders. That's to say, when we do quantum error correction experiments, we have measurements. Those measurements need to be processed classically to infer errors, and that's what decoders do. And we also need theorists for specifying, like, hey, if you only have 8 qubits, you can do some clever construction with this code, and it still is fault tolerant. I haven't mentioned what fault tolerance exactly means, but why didn't you do this? So this is a fruitful area, I would say. And you could say that one of the holy grails, I think there are many, many holy grails and stages, but the sort of earliest one, first one on the horizon, is sort of this where you show that adding redundancy helps, said simply. Because this, and I think you should think about this by itself is actually non-trivial, right? Because you could say, well, yeah, if I replace 1 qubit by, say, 7 qubits, and these 7 qubits together represent 1 logical qubit, then I multiply my error rate by 7, right? Because, well, now there are 7 places in which errors can happen. So how can these possibly be better, right? So it can only be better if I know that some errors that happen on those 7 qubits, I can actually deal with them, I can correct with them. But if I have to do that I'll, this correction itself, and actually figuring out where the errors happened, takes additional infrastructure, additional qubits and Scillas. These can also have errors, and so on. Right? So this is a non-trivial concept, if you may have heard about this already. And so this is sort of a phase transition, and you could say, we have to create a new phase of matter. It's not a phase of matter in any passive sense, because it has to be a computational phase of matter, right? And so if you see here, I don't know if you can read this, but this is a paper by the Google team from July this year, or last year, sorry, 2022, suppressing quantum errors by scaling a surface code logical qubit. And this was actually the first paper in which they said, we add more redundancy, and then we check we consider whether we actually lower the logical error rate. And for this this scheme, and they're kind of like borderline. You know, they say we need to really improve our basic error rates on the physical qubits by quite a lot, but by quite a factor still, in order to really get an improvement. But this scheme that they look at uses what's called a surface code. And I want to just show, I'm actually not going to talk about, I'm going to try to avoid talking about the surface code. And this is, I usually talk about surface code and I'm completely fed up with it. So, but who has, I just want to take a show of hands. Who knows the surface code? Right, okay, so this is, well, half the audience perhaps. Okay, so a fair number. All right, so the surface code is a favorite scheme in the experimental realm, but not the only scheme for doing quantum error correction. And it's something where you take 9, so a small surface code is something that looks like this. Well, what is this? I take 9 qubits, and they're located at the vertices of this lattice. And these black and white squares and half squares, or, you know, they are protocol, they describe what thing I have to measure. So a white square, for example, means I have to measure the parity of the 4 qubits at the corners of this square. And a black square means I have to measure the X parity of the 4 qubits at the square, and the X parity is the eigenvalue of the Pauli operator X, 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 X. And these things on the boundary is, you know, you have to measure the parity of these two of these 2 qubits. And so the point is that if you measure, if you're an eigenstate of all these parity checks, then you're in the code space. And this code space is 2-dimensional, so there is something you call 0 and something you call 1, and I can have a superposition of it. And I'm trying to keep my state in the code space, or at least what I'm trying to do is by repeatedly measuring these checks, I'm trying to figure out, oh, did it move out of the code space? And if so, by what error actually? And then if I just write that on a piece of paper, or I could apply the correction, but I could also just write on a piece of paper, then in the end of the day, I know, oh, okay, I've had errors on, you know, this qubit, that qubit, that qubit, that qubit. And, you know, then at the end of the day, maybe I measure all my qubits because I want to sort of, you know, measure my logical qubit. And I can use that information then to figure out how to, you know, how to read out the measurement. That's to say, I measure every individual qubits, and then I use all this parity check information to say, oh, I should really be reading this as I measured the qubit in 0 or in 1. Depending a little bit on what I do. Okay, I'm going a little too fast to other things, and I said I wasn't going to say much about the surface code, so let's not say more. But so here you see 9 qubits, but you can take a bigger surface like this, and that's kind of what they've done. They did experiments on a chip where they could embed this lattice of qubits with extra ancilla qubits that are used to measure these parity checks. So it's not just these qubits that you have to have. But then they compared the performance of this with this, and they saw that this was slightly better, but sort of like on the edge of, right? All right. But they are really the sort of furthest advanced in this, so that's why I'm showing this. All right. Okay, so now let's go back to what you're sort of going to be hearing this morning. And it's a vast area, and one has to decide to take some sort of, you know, some subjects out of this. I cannot, you know, discuss everything, obviously. And like I said, I want to avoid talking about the surface code. Usually I talk about surface code because this is this experimentally most favorite scheme, so people are interested in understanding the details of this. But there are also some technicalities which are maybe not so important. But I'll just sort of gloss over this. Okay, so the first part of the lectures, I want to talk about stabilizer quantum error correction. So this is stabilizer quantum error correction. It was invented by Daniel Gottesman in these early 90s, and has become sort of a favorite way of constructing codes because of, you know, its simplicity. But I also like to pause and throw in some things where we can think that maybe we should sort of go beyond stabilizer quantum error correction in the future. And there are already some efforts beyond this. Then I'll discuss this notion of fault tolerance, because there's always a lot of confusion about fault tolerance. Experimentalists ask me, like, what is this fault tolerant? And they say, well, okay, against what, right? And so I try to give some comments why there's this confusion, perhaps. Then in the second half, I'd like to just discuss some code constructions, in particular discussing a bit the connection with homology. And maybe if I come to this, some practical aspects of quantum error correction that are of recent interest of mine and of some other people relating to leakage. All right. So everybody good so far? Oh yeah, there's going to be some moment where questions are asked. I guess that's the most feasible with this large audience. Okay, so usually I have this slide that says, what's a subspace code? Because people are like, oh, what's a code? It's kind of complicated, idea, but it's actually very simple. I say, well, it's a subspace. Okay, done. Okay, so we have n qubits. We specify some two-dimensional subspace. But of course, the specification, if I don't say anything else, would typically be very inefficient, right? Because I have to kind of write, my basis vector spanning the space in terms of my n qubit states. And these will be highly entangled typically, so that's not efficient. So really the stabilizer code formalism, one of its advantages is that I have an efficient way of specifying this subspace. So let's say I encode a qubit, I could also encode many qubits. Usually I encode k qubits, a code, yeah, so then this subspace is to the k dimensional. If I encode k qubits. And then in usual notation, we have these bars. So the logical qubit states 0 and 1, if I encode one qubit, are given like this. And then, of course, I can also specify some operators, which should be, having the algebra of the Pauli operators on this logical qubit. So they should anti-commute, and they should have the operations as we expect them from the as Pauli operators. Right, so this is, and so the whole point of this slide is that it's a subspace and there are bars on stuff to distinguish it from physical qubits. But really, maybe the more modern view that we should sort of get into, although I'm not sure we have really gotten into this, or I know how to get into this, but of course you are young people, so maybe you'll get into this, that in some sense it's a robust channel for quantum information to flow from past to future. This is what we want to design, right? We want to push quantum information forward in time. You can also say, can we push quantum information backward in time, right? Because usually, laws of physics are, symmetric with respect to time evolution. Although I'm not sure that, this is actually a feasible idea. But I have also this idea of robustness. Right? And this relates to errors. Now, so you could say that if we look at physical systems, the native quantum dynamics that we have is sort of expanding. And expanding, I mean, there's always a new degree of freedom to interact with. Like if the system were to interact with the same degrees of freedom, then of course that would just say, oh, well, then describe it as a unitary, and that's the evolution, and it's kind of a closed system, or at least, I could see maybe, maybe in the next 10 hours, I need to include these degrees of freedom, but that's it then. No? Then I'm done with the degrees of freedom that will influence the system. But that's not the way the world works. We keep bumping into new people. We keep interacting with new things all the time. Right? So we couple to ever more degrees of freedom over time, and they give us pushes, they give us errors because their state wasn't included. We didn't know what they were doing, and they will influence us, and that effectively models noise. And so what we want with that system, we want to get a system that effectively flows as an approximately closed system. Right? That's sort of the task. And in error, so the point is to stress this perspective is that if I talk about a code, it's a spatial object, whereas what I'm trying to engineer is a construction that has a space-time coordinates. So maybe we should start with that instead of the spatial object and say, hey, but how do we measure these parity checks actually, and how we do this fault tolerant and everything. All right. So, so the idea then that come out of fault-tolerant error correction is that what the information is that we want to, that has to flow, has to sort of flow straight, like undisturbed, has to be small compared to degrees of freedom that I'm using, right? So that's the encoding. I can code 1 qubit into many. And secondly, that this rate of expansion is limited. So that's sort of the rate of errors is small, and the errors are also local. The chance that I'll have an error that messes up all 7 qubits is p to the 7th, where p is the probability that I mess up 1 qubit. And that's an essential concept in error correction. So if I didn't have that sort of, locality, the idea of small errors having higher probability than high probability errors, error correction would not work. All right, and the other thing, so that's encoding and the structure of the noise. The other thing that we use is classical monitoring. Now that's not an absolute necessity. People have worked on a concept called self-correction, where you're trying to design a system that innately suppresses the buildup of error and allows the sort of forward flow of information. But for what we call this sort of called passive error correction also, but for active error correction that I'll focus on in this lecture, is we measure these parity checks. So we have classical monitoring, and we have the help of our decoders, meaning they could be people or they could be algorithms, right? I mean, so there's some classical involvement, but there's also a price actually we pay for this classical involvement. And this is maybe also something that is, developing, coming in the future, is that it takes some time to measure. Now, there are some maybe fundamental limits, but it's also something that's practical. If you look at, for example, this Google experiment that I mentioned, they say that, one of the bigger contributors to their noise, maybe not there are many contributors, but one of the contributors to their noise is that, qubits decohere while they measure other qubits. The measurement takes like 500 or 100 to 500 nanoseconds, and sometimes longer. And the gate time takes like 20 nanoseconds. So measurement is relatively long, at least in that architecture. You have to be careful not to, to generalize to do everything. And then in addition, this decoder, if you measure all these parity checks in maybe 1 microsecond, then this leads to a lot of information that has to be processed by this decoder, right? And we are very powerful in terms of our classical computation, but maybe, question is, are we powerful enough to have this decoded on time if we have large codes doing very reliable computation? Right, so there is so in terms of these holy grail and stepping stones, there are also things that depend on this classical monitoring and processing. Are we fast enough? All right. Okay, so now just want to break. So what I want to do now is to give just basically what are stabilizer codes. Now that maybe is clear to some of you. But I do want to give it as a as a basic thing, because I think if you haven't heard about error correction, this is the thing to learn first and play with a little bit. Okay, so stabilizer codes, the essential things, we kind of have 3 groups of Pauli operators. It's all centered around Paulis. And the first one is the Pauli group. So we have n qubits, and we just take products of the Paulis and the identity, X, Y, Z and the identity. And because to make it a group, you also need some phase factors and so on, but that's not actually essential. Usually if we talk about a Pauli, we just sort of omit that part. And so there's some notation also. We write tensor products. Sometimes I'll write them this way, or sometimes I'll write them that way. And this Pauli group is sort of the blue stuff. And then what we're interested in is some subgroups. The first subgroup is the stabilizer subgroup. It's abelian. Everything commutes is an important property for some of the things. And it's generated by some subset of these elements. Let's call them S1 to Sn minus k. and we write it like this. So these are the generators. And typically, the idea of codes is that that these generators are acting, well, would be nice if they act on a few qubits. That's to say, I'm trying to encode k qubits into n, and these stabilizers, these generators, act on order 1 qubits, like 4 in the surface code. And those and say every qubit also participates in order 1 of these generators. Those codes are called LDPC codes, and there has been recent development, quantum LDPC codes, low density parity check codes. There's been recent development constructing those codes that you may have heard of. All right. Why do we like them to be, acting? Why would we like the generators to be acting on a few qubits? Well, we have to measure the eigenvalues of these generators, because the code space is actually an eigenspace of these generators. If errors happen, we want to be able to, by measuring the eigenvalue of the generators, to detect and correct the errors. And to measure the eigenvalues of generators that act on many, many qubits involves interacting with many, many qubits, and therefore is more complicated and more prone to errors. All right, so that's so the point is that your code space is the eigenspace plus 1 eigenspace, because the eigenvalues are plus 1 minus 1, plus 1 eigenspace of these elements. And then what else do we have? Okay, well, we have something we call the centralizer, which is all polys in the poly group which commute with elements in S. Okay, so let's think about that for a moment. This could be elements in S itself, of course, because S was abelian. But there could be more elements that were, that were not in S that have that free property. Yeah, and those I call logical operators. And it turns out you can characterize whatever they are as in some sort of a pair construction. So you can, the C of S is generated first by the stabilizers generators, and then there are these pairs. Xi and Zi, and so the mutually anti-commute, showing that the whole thing cannot be in S, and there will be k of them. And where they are, that's this, C of S is including all the yellow stuff and the red stuff. Okay, so these are the logical operators, and then what else can there be? Okay, so other things like a poly operator P, which is over here, so it's not in CS, obviously has to anti-commute with an element in S, right? They anti-commute with at least one element in S, and therefore they actually map a code state onto a state outside the code space. That's to say, because they anti-commute with the element S1, then you can verify very simply that they will flip the eigenvalue of S1 from +1 in the code space to -1. Right? So these are the errors that we can detect. Okay, so let me just repeat that. Okay, the code space is the space for all elements in S. Nothing happens. And we can take an example. For example, the two checks or the two generators are XX and ZZ. Then it turns out that C of S is just S itself. There's nothing else that commutes with XX and ZZ and is not already generated, right? What commutes is YY, but that of course is the product of XX and ZZ. Yeah. So then the code space is one-dimensional. It's just a state. So that's also possible, but of course we want to encode a qubit, not just a state. All right, so you can actually prove that if you have n minus k linearly dependent generators, you encode k qubits. And some of the jargon that I'll be using, these generators of S are called the parity checks, the X if it's only a product of X's, Z if it's only a product of Z's, or the check operators and things like that. All right. Yeah, so now one word still about why the logical operators are in C of S. Now, what is required of these logical operators? That they have this algebra of the, that the separate qubits would have. And that, of course, they, x, say, on 0 maps it onto 1. And if I apply S on it, then, of course, I should still be in the code space, because otherwise, if I'm outside the code space, I'm not getting the right action. So what you need to have for the logical operators is they need to commute with elements in S, but they should not be generated. So there's a quick argument you can try out on yourself whether you agree with that. All right, so let's take a small example, which is the smallest sort of code, which is very, very simple. And so in this code, the S is generated by, so we have 4 qubits, and S is generated by XXXX and ZZZ. So then the first question is, how many qubits does this encode? Well, I gave you the formula, so I have 4 qubits, I have 2 independent checks, so I encode 2 qubits. Yeah. So now I have to find, so then I say, okay, I have to find 2 pairs, 2 logical qubits, 2 pairs of, x and z's. So for the qubit number 1, I have to find the logical x and the logical z. If qubit number 2, I have to find the logical x and the logical z. And they have to commute with everything here. And they have to follow some particular mutual anti-commutation and commutation relation. Okay, so now if you think about what commutes with this stuff, of course, if I do a poly X on any of these 2 qubits, it will commute, right? Because the important rule is anti-commutation twice leads to commutation. So the one choice of the logical operators are, for example, the logical X1 is XX identity. Now I need to get a logical Z that also commutes with this, but anti-commutes with that. So this is a choice, and I can similarly do this. All right, now that leads us to another concept which is essential to characterize the code, which is the distance, right? There are 3 parameters. There's the number of physical qubits n, there's the number of logical qubits k, and then there's distance. This is not, of course, there are other features of the code that go beyond this, but these are the 3 first parameters you want to give. And the distance here is 2, and this means, what is the distance? It's, I look at all elements in CS, but are not in S, and I just say, what's the minimum number of polys on which they can act? That's the distance, essentially. And here, I can move the support, like I can move this, XX identity, I can multiply with this, and then it's XX on the last 2 qubits, but I can't change its weight to 1, because it's clear that any single qubit poly will anti-commute here. Right, so the distance is 2. All right. Okay, so now this is one important thing about what the errors do. Okay, so now what we can say, okay, now we have everything else that is in blue, but not in the yellow stuff and or the red stuff, and those are the errors. And so they'll anti-commute with at least one element in S. Okay, so, well, either E commutes with all elements S, so E is in there, okay. Sorry, I shouldn't say it this way. Okay, so I have a poly E, we consider it a state. Okay, what are the possibilities? Either E is in CS. Well, if E is in S, it doesn't do anything on a code word, so fine. But if E is a logical operator, this is bad. So, for example, for this error, this code I just discussed, if by some reason the environment does XX on the first 2 qubits, it does a logical error, and I'm still in the code space. So if I measure the parity checks, I'm not going to detect this, but my information has changed, and this is very bad, of course. This is not what I want to have happen. Now, of course, then, as I already mentioned, in the other case, I'm in this stuff, and then I will anti-commute with some S, and then I can have this, so the eigenvalue of this S will be -1, and we detect the error. So, therefore, a stabilizer code of distance d can detect all poly errors of weight less than d. Right? Nice. But detection is not quite correction, as we'll see in a moment. So this is some notation that we use, NKD, and so we got the 4-qubit code, we got the Shor code. So these are the earliest codes, the Steen code we'll see. And the smallest code correcting a single error uses 5 qubits. N is 5 and D is 3. Okay, so this already suggests that the distance is not quite like, the distance -1 is not the number of errors you can correct. And that comes now. Okay, so let's talk about this measuring of these parity checks. So this also has some names associated with. So we measure the eigenvalues of these stabilizer generators. I've denoted them with this. This is a slightly different font. And they together form a vector, and that vector is called the syndrome. So that's what we learn classically. And based on that syndrome, we have to find out what errors have happened, right? And then we have to realize that there may not be, for every syndrome that we find, a single error that can cause it. There may be that error or that error. And this is something that I have to resolve because, for example, if it's that error, but the difference between the errors is a stabilizer or the product is a stabilizer, then it doesn't matter whether I choose that or that. Because clearly, if that one happened, and now I correct with that one, I've effectively applied a stabilizer, and that's the code is invariant under that stabilizer. So that's good. That's the good case. But if there's another scenario in which error E happened, but there's another error E double prime, which the product of them is a logical operator. That is a bad case, and these are actually the only cases you can verify if they have the same syndrome, the same eigenvalues, then these are the only 2 cases that can occur. But in this last case, I have a problem, right? Because then the error E happened, I decided for E double prime, and effectively I've done a logical without knowing that I did. So this is what I have to avoid. So how can I avoid this? Well, ideally, I would do something and say, well, I choose the error with the highest probability that could lead to that syndrome, right? But then if there's not one error that could do that, I can say, well, then I have to sum the total probabilities for errors that could lead to the syndrome. But then I have to have different classes because one set class would be the errors and all the errors plus the stabilizers that could lead to the syndrome. And another class would be those errors, but then with a logical applied to it. And I have to say, well, is the class where I apply the logical, is that a higher probability than a class in which there's no logical? That's the decision that I have to do. That's maximum likelihood decoding. But the problem is that this is sometimes inefficient because there will be many errors. The stabilizer has many generators. So every error I can multiply with all these stabilizers. And they're, like if I have n qubits, there are order n of them. So this is 2 to the n possible or 2 to the order n possible stabilizers that I have to multiply with. So maximum likelihood decoding is typically not efficient. And then you say, well, but if I multiply an error by a stabilizer, maybe then that I get a high weight error, and high weight errors are unlikely. So I don't have to execute this whole sum. And I'm just doing something called minimum weight decoding. And there are many, many other code decoding strategies or optimization, because it's just some optimization problem you have to solve. So minimum weight decoding, I'm saying, okay, I got a syndrome. Now I'm just trying to pick a Pauli error that has minimum weight, acts on the fewest qubits that can lead to this error. Okay? So that's one strategy you could do. And then, if you do that, you have the following almost trivial statement. If you have a code of distance d, which is 2t plus 1, it can correct any error of weight t by minimum weight decoding. So what you do is you say, okay, an error of weight less than t happened. Okay, I'm going to decode. Now, there will be that error I could choose, or any error that is even, of lower weight. So that means that the product of those errors will have weight at most 2t, right? Because both of them will have weight less than t. But anything that the product of, any poly that has weight 2t cannot be illogical because the distance is 2t plus 1. So I'm always good. So that's, well, this is what I put down as a proof. All right, so that's where the distance comes in, that it says by minimum weight decoding that you can kind of correct, half the distance of errors. All right, but minimum weight decoding may not be your favorite decoding model because, well, the point is you have to let your decoding depend on your noise model or your errors. And actually currently in experiments, they say, well, we can have predetermined noise models from theory, like depolarizing noise and things like that. But we could also do experiments by which we figure out the noise model. We figure out what are likely errors, and we use that for decoding. And that can be a better strategy because sometimes the noise varies in time. Like today I calibrate stuff, and tomorrow it looks slightly different. And so maybe I want to put that information in my decoding. And it also allows you to kind of see, deviations from what you expect theoretically, which is a problem in, devices. They're sometimes crosstalk 2 qubits, interact via a 2-qubit gate, whereas they should just be sort of idling by themselves. And so those things can be determined and used then. All right. So one little thing about erasures. So if you want to, so we just argued that a code can, correct errors of weight t, and d is 2t plus 1, but we also said that we can detect any error of weight less than d. So then that means that if we also, let's say we can detect any error weight less than d, but we also get a flag, we have erasure errors. And erasure errors are errors in which I get a flag that's, there was an error. An erasure error is essentially, I have a qubit, it leaks, maybe it goes from out of 0, 1, it goes to some higher dimensional space, and I get a flag that says, I'm leaked, I'm bad, or there's something else that happens with the qubit, maybe there's an error that I've detected, and that will be sort of flagged. So the decoder gets that additional bit of information, so it can use that and say, oh, well, but then I know that the syndrome must be due to that error, at least if it's consistent, and I can use that information. I don't have this ambiguity of which, error pattern I have to choose. And strictly speaking, an erasure error is an error in which a known set of qubit is lost, and then to say it's replaced by the completely mixed state, right? Okay, but let's see how this works for the 4-qubit code. So in the first case, I'm not getting any erasure information or anything, and I just have a single error happening, x on the first qubit, and it happens on the state, on this state. I don't care what state I have. But it's clear if I measure the eigenvalues of these checks, this one has +1 eigenvalue, and this one will have -1 eigenvalue because it anti-commutes with this x1. So now I can detect the error, but of course I have no clue whether this was an error on x1 or x2, x3 or x4. Any of these 4 possibilities would have led to this syndrome. And so, for example, I say, well, I have no clue, so I'll just pick a random one. I'll pick x2. And then after error correction, the error x1 happened. I did apply x2. And then I can double check that x1, x2 was what I called before the logical x operator. Yeah. So now I made this logical error. I'm in this bad case in which there were 2 errors that both could be leading to the syndrome, and the product of them is a logical operator. Okay, but now consider another scenario, in which besides, we just learn. There's no error it's particularly happened. We just learned that qubit 1 is leaked or lost. And it has been reset. So it's put somewhere in the computational space. Maybe we don't replace it with a completely mixed state, we just set it to 0 or something. Then we measure the eigenvalues of the old z operator. And we find it comes out -1. Note that it's not predetermined will come out -1 because putting that qubit in a completely mixed state or 0, it depends. It's no longer correlated with the other things. So it probably will, with probability half, it comes out, this ZZZ comes out +1 or -1. So let's say it comes out to -1, then actually we sort of project it into a certain error. And then what we do is we'll conclude we should correct with x1 because we know that there was trouble on qubit number 1, right? Of course, this assumes that, you know, there is no other errors are likely to occur on the other qubits. I mean, this shows that if I had also probability errors on qubit number 2, and they occurred with equally likelihood as this qubit being lost, then I'm in trouble, right? Because then I say, well, okay, it could be that qubit number 2, or it was the loss of qubit number 1 that I've learned about. But if the probability for an error on the other 3 qubits or a regular parallel error is like an order of magnitude lower, then I say, well, okay, the most likely thing, it's really that qubit number 1 that was bad, and I'm going to do my correction there, right? But of course, I will make some small error by doing this because there is a chance that, you know, the other guy was bad. All right. Okay, so now a little bit on... So I said we have to measure the parity checks. We have to measure the eigenvalues of the stabilizer. How do we do this? Now, one can spend quite a bit of time explaining this, but I'm just giving you one little circuit, which is over here. If I have a unitary, which has eigenvalue +1 or -1, for example, a poly, then I can always use this circuit to measure the eigenvalue, and the eigenvalue answer will come out here. Okay, so nice. I can apply that with, for, you know, poly being, you know, x, right? One of these checks. And then this controlled, all the x's, we can break it down into 4 controlled knots, because the knot is the x operator. And so you can do this with all these checks. And then, of course, you can ask about errors that occur in these circuits. Okay, so we'll come back to some fault tolerance after mentioning... Yeah, so I just want to make a comment about logic that we need to do. And then I want to come back to fault tolerance, basically, as the final thing. Actually, maybe I should pause for a moment if there are any questions here so far. Yeah, there's a question.
Okay, thanks. Let's say we have a 4-dimensional space. We want to encode...
4-dimensional what?
A 4-dimensional code space, and we want to space 2 qubits. Does it matter in the sense of code performance, which logical operators we want to choose, or is there anything gained to choose those logical operators based on noise model at hand?
You mean you want to... So you don't want to necessarily use a stabilizer formalism, but just more general?
Right.
Yeah, of course there are choices that... of course, okay, so there are... Okay, so you go within the stabilizer formalism, you say, I want to create some, you know, 4-dimensional space. Of course, you know, there is... If I use more redundancy, I can have a code with higher distance. But then here I assume that there are poly errors, but there are also qubit codes in which I focus on correcting amplitude damping. And like say the 4-qubit code can correct one amplitude damping error, whereas it only detects poly errors. But I don't know if that's your question. And then of course there are, you know, other types of noise, but then you start with like, you know, bosonic system and other things. Does this answer your question?
Yes.
Yeah. Of course, this is very focused on poly errors, and if people know more from physics, they say, well, that's not a very natural noise model because I have T1 and T2 and so on. But there are, you know, ways in which we convert these things. Any other question? Oh, here's a question.
So this may be a very naive question, but in the first slide, you mentioned a paper of 2022 where it expands the distance 3 to distance 5, and the logical error rate decreases.
Slightly, yes.
But there are many papers before it, like Fowler's 2012 paper and other papers who have shown that distance 3, 5, 7, and as the distance increases, the logical error rate decreases. So
this is experiment. Yeah, the good question. So the Fowler papers, that was all numerical simulations with the polarizing noise and so on.
Yes.
And this is experimental data, right?
Okay.
Yeah.
And I have another question of minimum weight perfect matching, the decoder. Minimum
Okay,
weight
the
decoder.
minimum weight decoding is not minimum weight perfect matching. Huh? So the minimum weight perfect matching is a decoder that is very specific for the surface code.
Yes. Okay. So for minimum weight decoding, so it detects the minimum number of errors. So if I take a larger distance error, suppose distance 5 surface code or topological code, then between suppose up 1 qubit error gives a syndrome and a 2 qubit error gives same syndrome, then the decoder will always detect the 1 qubit error.
Yes, then if that minimum weight decoding, well, if you do minimum weight decoding, we'll take that 1 qubit error, yes.
Yes, okay. So it can never detect the 2 qubit error.
No, it's not. Yeah, it will decide for the single qubit error, indeed, yes.
Oh, okay.
So it will not decide for the 2 qubit error, but the point is that so the point is with this like a surface code, okay, so then if these errors are in disjoint qubits, the product will be a weight 3 error, and actually in the surface code there are no stabilizers of weight 3, so this will not happen, but in the surface code there are stabilizers of weight 4, so there are very often cases in which errors happen sort of here and there, and you actually pick the error for this, you pick this error and the product of them is a stabilizer, but this is completely fine.
Okay.
Yeah? Yeah. Yeah. Oh, okay, well, that's good.
A couple of slides back, you outlined a situation where you find out that a particular qubit has been erased, and then you apply a syndrome measurement to sort of work out what the error could have been. What's a practical situation where you could learn that a specific qubit has decohered without having done stabilizer measurements?
Sorry, say it again. What is the procedure?
So okay, so I think
I know what you mean.
Yes, number 2, you learn that qubit 1 is lost, and then you measure a stabilizer to work out what error might have caused that. How would you find out that qubit 1 specifically has been lost, if not by doing stabilizer measurements?
Well, you would not. So this is a very good question. I mean, there are actually studies which say the leakage of a qubit would lead. See, the point is, depends on what the leakage of the qubit does when I measure the parity checks. Okay? So, for example, I have a parity check and I'm entering, you have a qubit that's lost and there's a control Z happening with the ancilla. And then, because the qubit's lost, maybe the ancilla gets a different phase shift, not a ZZ, but it does something else. Or it gets no phase shift. And that determines what is the signature of leakage, right? So it's not a priori, I was going to say something about that last, but I can say as well. The signature of leakage depend on the experiment and on further details. The codes, there's some, I have to maybe go. What? Yeah, because I'm close to I think there's some, or not. Is that what it is? Anyhow, so the signature of leakage is not, I was just talking into the mic, I guess. The signature of leakage is not a priori clear. It's not designed to be detected as a clear syndrome and say, oh, that's leakage, right? And but you can still think about it, and you can still sort of machine learn. You can look at the syndrome that you get and see what are the signatures of leakage, and can I learn this, right? Can I learn what are typical patterns of syndrome measurement I'll get that are corresponding to leakage? And that's what people also are trying to do. But of course, it would be nicer if you can detect the leakage right away, if that's possible. Yeah.
Okay, thanks.
Yeah. All right, so let's move on. All right. Okay, so let me just look at so I have 2 slides on encoded logic, so I still have, see how we get to the end of this before I have a break. All right, so at the beginning I said, besides from encoding, we also need to do logic. And you may know that to do logic, we can use a universal set of gates that uses the C0, the Hadamard, some preparation and Z measurement. And then on top of that, we need the T-gates. And there is this important concept of the Clifford group. So the Clifford set of Clifford gates and all these, C0, Hadamard, and Pauli's are in the Clifford group. And if I have a circuit with only Clifford gates, I can classically simulate it. And they are unitaries that if you conjugate, let them act by conjugation, you get another Pauli. And so there's a Clifford hierarchy that which is like CK, and C2 is the Clifford group, C1 is the Pauli group. So they're further unitaries. We act by conjugation. You map Pauli's to element in the lower sort of one. So for example, the T-gate is in C3, meaning that if you conjugate a Pauli, then you conjugate, you let C act by conjugation on Pauli, you get a Clifford gate. All right, and that's the one that we need. And okay, so here are the gates. And the point is now, just to discuss very briefly, what is required to do logic. And this is a whole subject by itself, so I won't say too much about it. But then what we like, ideally, is that all the logical gates are what we call transversal. And here's a picture. So we have two code blocks. Say I use a Steen code, which is encoding 1 into 7. This is a picture of the Steen code where there's 7 qubits and every face is both an XXXX and a ZZZZ. And Steen code is the smallest code over two-dimensional colored code. Okay, so I have these two blocks here. I only have 3 qubits, but imagine there's 7. And then I want to do a C0 between these two blocks. And if the C0 gate's transversal, which is true for the Steen code, I can just do a C0 between qubit 1 on this block, qubit 1 on that one, and 2 with this 2, and these 3 with this 3, and so on. So I partner the qubits. And the nice feature about this, there's 2 things. One is that it has steps 1, right? I could do all these gates in parallel. And secondly, if a single error happens on this qubit, on the C0 or on any of these qubits, it will not spread to any other qubits in the block. It will spread, or there will be an error on a qubit here and a qubit there, right, in the separate blocks. But the Steen code is one in which I can correct 1 error. It has distance 3. So 1 error in the block, I can still correct, right? And so that's a nice construction. Yeah, and so the problem is, if I look at other gates for the Steen code, for example, the Hadamard is good, and the S gate is also transversal. So this is a nice feature of the color code. In 2D, all Clifford gates are transversal. But if I do the T gate, so if we look at this circuit, here I intend to do a T, and the L stands for logical. And I can do that on my Steen code by this little circuit. And you see this little circuit is on 7 qubits, and it takes a bunch of C0s. And then we can see what happens when there's an error. For example, there's a Z error there. And you can look at the propagation of the Z error. Let's just say you sort of commute it through these C0s. And then you can find that it actually becomes a Z error on 3 qubits because it propagates through these, these target knots. And this thing is a logical Z. So the problem is that a single qubit error can become, through propagation, a logical error. And if this circuit cannot tolerate single qubit errors, well, then it's a bad circuit, because it's certainly not going to be operating more reliable than a single T-gate on a single qubit, right? Because it's even harder to get the same fidelity of these operations than on a single qubit. So that's no good. So the problem is that for the gates, so there's some theorems that say we cannot have all the gates for universal computation be transversal or sort of easy. There are other ways to do this. We use code deformation. And so we need other constructions for the non-Clifford gates, typically. This is also true for the surface code. And these add some overheads. But there's not, and people have looked at, different schemes for this and try to optimize this. It's not so easy. All right, so now let's just discuss fault tolerance a little bit and come to this threshold theorem and kind of, actually, so I want to state the concatenation part. Now, this slide and the construction is sort of coming out of early error correction theory. It may not be the way you think about it or the way you've learned to think about it if you know the surface code and things like that. And it's sort of also not entirely ideally suited. But let's say I want to do an experiment in which at the physical level, I would be having a qubit in 0. Then I do a unitary gate, and then I measure that qubit in the Z basis. That's my target, say. Now I want to do the encoded version of this. And I want to argue mathematically that the encoded version has, for low enough error probability of my basic circuit, it possibly has a lower logical error rate. So, sorry, say this again. Okay, so you can see if I have a very simple case, I say, okay, every step here can fail with probability P, right? So what's the probability that the whole thing fails? Well, that's sort of like, 3p, 1 minus p squared. And that is less than 3p. So, of course, if I make this circuit longer, it will be something like n times p. That scales with. And now my goal is of my encoded circuit, using a small quantum error correction code that can correct a single error, I want to get something that scales like 3 times p squared. And it scales like there may be a constant in front. And of course, if the constant is very large, then 3 times p squared can still be higher than 3p. But if p is sufficiently low, 3p squared will be less. And that's the goal, right? That's the goal of encoding. And if I had n steps, I would want to use this code that corrects a single error. I would want to have some procedure that the error scales like m times p squared. And then we compare that with n times p. Yeah, and then of course you see, well, okay, but if n is very long, n times p squared is still terrible, right? So you say, well, what have I gained? Now, then it's obvious, they say, well, I should actually kind of repeat this thing in the sense that I've replaced sort of every one of these operations by some unit that had sort of scaling like p squared. And then if I look inside that unit and look at the elementary operations, I can again do this and get an enhancement. So that's the idea of concatenation. Okay, but now let's look at these units. So now instead of just preparing a state in 0, I'm going to do some preparation of the logical 0 and something I call the QEC unit. So this is a unit that I can define that has to have a certain functionality. And the functionality is sort of like if a single error comes in, it should correct the error. If no error comes in and there's a single error in that unit, there should be at most a single error on output. Right? It has to have these kind of fault-tolerant design rules. And design rules, if it obeys these design rules, I want to use that argumentation to say, hey, I will get an error that scales like 3p squared. All right. Now, just about what is required in these units for this design rules, these fault-tolerant design rules to be obeyed, and for the error probability to scale like 3p squared. Sort of a few sort of failure modes, that's to say. Now, let's imagine, of course, I already mentioned, if the gate is transversal, if a single error happens in that gate, then it will spread, and I have only a single logical qubit, it only stays on that single physical qubit. So if a single error happens in the gate, and this QEC cycle is perfect, so no error, then it will get corrected. Yeah. So this is fine, right? But then let's talk about the quantum error correction cycle. Now let's say in the quantum error cycle, I was measuring stabilizers and executing this circuit. And in this quantum error correction cycle, there was an error. Let's say it's this X error. And then you can see this X error will flip the control of these C naughts, and it will become 2 X errors on output. This is sort of a short way of writing that on output I have this doesn't lead to any flip here, but it leads to 2 X errors. So the quantum error correction has a feature that a single error in the block may lead to 2 errors on output. So if I would follow it by another quantum error correction cycle, I may not be able to correct this because the code can only correct a single error. Now I say may because I've talked about distance as a rough metric, but a code that can correct a single error may be able to correct certain 2-qubit errors, right? And because, I just look at the collection of errors and I say, well, any 2 of them, could they lead to a logical, any 2 of them that have the same syndrome, could they lead to logical, then it's bad. But it could be that there is a 2-qubit error that is in that set that is fine. So actually, in the designing of this circuit, sometimes the order of the C0 actually matters in terms of making it fault tolerant, because of the nature of this 2-qubit error on which qubit it acts. One is good, the other one is not. All right. So, but one has to be careful, especially when this is like the C0s act on many qubits. For example, for the color codes, if you go beyond, the Steen code, there is codes in which you act on 6 qubits. There's the parity checks act on 6 qubits. And then you say, oh, and then a single error can affect 3 qubits. It's quite high. And then for small codes, which can only correct a single error, you really have to do extra things in order to make circuits fault tolerant because of this issue. Right? Because there's a back propagation of errors that are of higher weight than the one that you insert. All right. Now there's another issue which is of a different nature. We say, well, imagine doing this for n steps. Then I'd say, well, yeah, okay, code can correct a single error, but what rate of error how densely should I put my errors that I can correct? What should be actually the correctable set of errors? Because it's clear that if there's many errors and they all clump together or they're too densely placed, I will also not be able to correct things. For example, I could have an outgoing error on this gate, and then it's also an error in the QEC cycle, and they can combine sort of badly together to become a 2-qubit error that I can't correct. So just saying, oh, I can correct this, if I have a single, at most a single error in every one of these steps, and then, I can correct this, so my logical error rate will be p². That is actually wrong. So you have to be a bit careful, and this is what was done in these early papers. And they state the following statement. So they defined something like an extended rectangle. So I had these black boxes that were rectangles. Let's see here. These are these units. And now I define extended rectangles, which are like the black box plus the QEC unit before it. So black box plus QEC unit before. This sequence is slightly longer, just an additional identity gate. And so the claim is this. If there is at most one error in each extended rectangle, which precludes certain error patterns, right? Because, for example, having a QEC, having this an error and that an error would not be a single error in this extended rectangle. This is not allowed. I only have to allow to put one error here. Okay, so if there's at most one error in each extended rectangle, and everything is fault tolerant, according to the design rules, then the entire sequence will have no overall error. You can prove this. So every time you're doing a QEC cycle that corrects the error, you're doing it sort of, the errors are sparse enough, you can keep on correcting stuff. So this means that in order to fail, you just need to have 2 errors in any of these extended rectangles, right? So I have 3 extended rectangles. Oh, here I have 4. All right. And the probability for 2 errors in extended rectangles, well, okay, how many places are there for failure? And that choose 2. That's the number of that is times p². That is the probability to have an extended rectangle with 2 errors. So the point is, this scales like, some prefactor, which is a combinatorial thing, times 3, which is the length of this thing, times p², because I need 2 errors. Okay, so that's the idea. And I just wanted to flash this extended rectangle thing, because that, I think, sometimes leads to some of the, sometimes leads to some of the confusion. And also some of the studies that are a little bit, there is some subtlety, because if you do surface code error correction, if you're familiar with it, you say, well, what's the QEC unit here? Is this 2 cycles or 3 cycles? Because if I process my error information, I typically do decoding, which involves many cycles. Not an infinite number, but some kind of correlation length number. And that correlation length kind of sets this QEC unit, sort of how often it is. But the problem is that this formalism doesn't allow this QEC unit, like, this has decoding in it, to talk to this QEC unit and together decode. And that's what makes this a little bit awkward because you do decode a volume of space-time of a certain correlation length with, and this is sort of not so well matched for this. But at least it allows you to kind of mathematically make the statement that with fault tolerance, you can reduce your error from p to p squared, and then reiterate this, many times. Okay, so now I talked about the fault tolerance design rules, and this is just a slide flashing the design rules in pictures. For example, let's look at this. I prepare a logical state. In that preparation unit, whatever it is, there's some 2-qubit gates. If there's a single fault, a single error, it should on output lead to the logical state plus at most 1 error. And what is important to note is that these circuits can use 2-qubit gates. And we kind of say mathematically at least that, if such a 2-qubit gate can fail, it can put 2 errors after it with this probability p. And so we're not assuming that the probability that both qubits have gone some poly error is p squared. No, we assume it's p. So that's important. And of whether that's justified to some extent, because if you're trying to have qubits, well, first of all, this error model is far from experiment, because every operation has the same error probability p, which is of course not at all the case. Secondly, it's not poly errors also. And thirdly, you can imagine if you try to interact 2 qubits, you're doing, an entangling operation, that there will be correlated errors, and you should not assume that these are lower order than these sort of uncorrelated errors. Right? So that's a reasonable thing. All right. So now we're ready for this threshold theorem by concatenation. So you first say, in my example, I had 3 units, 0, U, measurement. So every unit or location I replace by a new fault-tolerant unit, which is like do the encoded thing plus a QEC unit with some fault-tolerant, which have fault-tolerant design properties. And then I look inside that circuit, and again I do this. And because that circuit has C0 gates that I can replace by the logical C0 unit with an error correction in cycle. And so the point is that the unit will have a lower error rate. Now, I said it was scaling like p squared with some constant in front. And this will be lower below some critical number, because we compare this with p. And then if we repeat this, and now what happens when we repeat this error times? Okay, so this is a little high. So if we do R levels of concatenation, we get an error rate of the whole thing of one operation. Let's say I take one operation, some C0 gate I had to do, and I do this R times. I get a logical error rate which scales like p times 2 to the r. This is the essential thing. It doesn't scale like p to the r, but 2 to the r. What am I paying in terms of overhead for this? So, for example, I had one C0 gate, and now I replaced it with some big thing which has S locations, right? The C0, maybe it's transversal, it's just sort of fairly slim, but maybe it's more complicated for a T gate. So let's call that size S, a circuit of size S. And that includes the QEC that comes after the gate itself. All right, so now what do we get? So what the goal is, we have to simulate an ideal circuit of size n. So there are n locations to do this on, right? And we want to use a noisy circuit, and we want the overall accuracy to be delta, right? Now, delta, so what is the epsilon that we need then, right? So typically, if the overall accuracy is delta, then the errors just add. So if we target a basic error rate epsilon, such that epsilon is n times delta. And then, so then if we just convert this dependence on delta and this expression here, we get this, right? That gives us R, right? Taking the log. And then we can also determine the overhead because we know R, so we can determine what S to the R is. And so the size, so originally I had n operations. Now every operation now gets sort of expanded into a big thing. And so n times S to the R, and that feels like this. And this is the basically point. There's some prefactors that depend on the actual error rate, how far am I below threshold, the constructions that I'm using, the overall accuracy that I choose for. But this is the polylog overhead. So instead of using n operations, I use n times log n to some power, where this depends on this S. So this is a polylog overhead, right? And this is important that this is not like n going to n squared, but it's fairly mild. But the problem is, one problem why concatenation has fallen out of favor, I think partially, is that this S can still be quite large. And so, that is still the overhead is large. And this noise threshold, right, there is this value why this, if you do this concatenation scheme, it depended on this PC, which is the critical sort of noise threshold, that is quite low. In these early studies, it was like 10 to minus 5, but these were very rigorous studies overall. And if you know about the surface code, you say the threshold is like, 0.8% or something. Okay, so that's the concatenation scheme. Now, if you are familiar with the surface code, it goes slightly different, so we can compare this. So if you have something like a surface code that encodes 1 qubit, so every qubit in your block is going to be replaced by some d squared physical qubits, and d is the distance of the code. And then without proof, I can tell you that if I do now a gate at this logical level, which is my sort of the unit I estimated before, that scales as the space-time is order d to the third. And space-time, I mean, it's I'm not making any distinction between how many additional qubits I have or how long I compute, right? It's a space-time volume that I'm taking. And the logical error probability for such an encoded gate scales like e to the minus gamma times d, and gamma is a parameter that depends on some specific of the code, how much you are below threshold, what is the logical gate we're actually doing, and things like that. Okay, so that's my epsilon. And now the space, again, I can do the same thing. So now my overhead is m times order d to the third, right? And operations at each costing order d to the third. And if I then, plug all this thing in, I get, well, this constant also depends on delta actually, but I get an n times log n to the third, right? So the point is that this log n to the log s now looks like a lower polylog, so to say. And one of the questions that was asked and partially answered by Gottesman later was, can you make this constant? So can this also scale like n times some big constant? And so this raises some fundamental questions. So for example, he showed in 2014, if you use a block code, so these schemes, like for the surface code, for every qubit that I read originally in circuit, I use order d to the d squared physical qubits, right? I encode it separately, but I can also take k qubits, or is my original circuit, and I encode them into n. And then what I like is I like my k over n to be a constant, right? And I like my k over n to be a constant, and ideally, I like my d over n to be also a constant. And I like my code to be LDPC. So this basically, the definition of a good LDPC code, quantum LDPC code is that my rate, k over n, is constant, lower bounded. My distance over n is also constant. And the code is LDPC, meaning that the parity checks act on few qubits, and every qubit is participating in few parity checks. These codes, at the time of his writing, they didn't exist yet, but you could actually relax this thing a little bit, in the sense that you know, the point is many codes can correct much more than the distance. So even if the distance is a lower power, it's not scaling like n, but like log n even, you can actually correct many more errors, and things would scale. And you also need an efficient decoder. So, but he proved you could have a constant space overhead, meaning that if you originally had n qubits, now you have, again, order n qubits. And this essentially, you would say, comes from this using these block codes, but you need a few more ideas here. But it didn't seem possible that you'd have constant time overhead, because when you have a block code, and this is another comment, so people have been developing these good LDPC codes and block codes and so on. It looks very beautiful, but the point is that it's much harder. Like if you do a computation, if you do circuits that you want to do many gates in parallel. But to do gates on encoded qubits in a block code in parallel is a lot harder. And of course you don't want to say, oh, well, or then you say, well, okay, I pull one qubit out of the block code and then do the gate and then put it back in. But then if you have to do that with all the qubits, then that's not efficient anymore, right? So you can do it maybe with blocks. But so from my perspective, I see the block codes, which is constant rate, more as a storage medium where you say, okay, densely stored, and then a subset of qubits maybe is pulled out, but that's a smaller set. And there we do the logic, the computation on. But we're not trying to do the computation while they're encoded in that sort of very dense code. Okay, so this is the thing, and so he left also an open question. He had some discussion about it. Can one simulate an ideal circuit with a noisy circuit with a constant space and time overhead? I think that seems overall hard, and it kind of feeds back to this original question about letting quantum information flow robustly, and what are the limits of that? What we can do? What are the sort of overheads in terms of extra degrees of freedom in space and extra degrees of freedom in time to accomplish this? Okay, but maybe there are new ideas that are possible there. All right, so I think we're going to have some questions now, and then I have I'll move on after the break. So questions, yeah.
Thanks. So did I understand this correctly, that the time overhead increases exponentially in the number of concatenation layers, but you don't need many, right? So that's the...
No, wait a moment. There is an exponential. I've mentioned this as a size. Yeah, indeed. Yeah.
So just like to understand that if we want to run concatenation, it slows down in every level.
Yes, okay. Because you need, and that is also true for the surface code that you're. So for some gates.
You don't need a large S.
Yeah, I don't know whether it is a fundamental thing. So for surface code, for some gates, the operations are transversal, so that's very fast. But then the QEC cycle still has to be repeated in order to be robust. So then that scales actually with code distance. And then for other gates, like the T gate, the constructions are even more involved and really scale indeed in terms of the depth also with D. But the point is that, you can, if you go to higher dimensional codes, you can, this repetition of the quantum error correction cycle, you can make constant, like you don't need to repeat it D times. But there is still the construction of the fault-tolerant logic. And so I don't know whether you can make this constant. Yeah, not 100% sure.
I heard somebody claiming the opposites at some point, and I was surprised. So that's why I asked. Thanks. No, I mean, somebody once told me,
yes,
if you concatenate, first level you concatenate, it takes longer, but like starting from there, you kind of doesn't get slower anymore. But that's
slower, wrong. But this is just...
Yeah.
Okay, I don't know. Maybe you should tell me more of what you're referring to, because it may probably make sense somewhere. Okay, yeah.
Thank you, Professor. I have two questions, one short, one long. The first one is to follow up on threshold by increasing distance. So in that size, you mentioned about the space-time size of the encoded gate. I wonder, when you talk about time, do you refer to the parallelism or parallel, like this ability to parallel quantum gates in one time size when you're doing?
Yeah. So let's see, which slide was this? About the.
Yeah, here.
This one, yeah.
Yeah.
I hear the assumption is that we can do sort of maximal parallelism, indeed. And what I mean by space-time is just that, okay, what's the depth times the number of qubits? And that's the size, right?
So
how
you
deep and how many qubits I have, yeah.
So you calculate the time size by counting the number of time sizes by pushing them as much as possible in one
Yeah,
thing.
yes, yeah. And also, yeah, indeed, yeah.
And I have a longer question about code deformation. So we understand that, for example, for Stein code and quantum Reed-Muller code, you can do code switching fault tolerantly. However, this kind of operation requires gauge fixing, meaning you have to perform measurement. And you mentioned that sometimes measurement takes time, and qubits, while waiting for to be measured, they will decohere. So I wonder, thinking about this, is it still naive to use code deformation as a way to circumvent the no-go on transversal
No, well,
gates?
okay. So, the code information also used in the surface code to do the C0 gate. And there, it's sort of part of the integral QEC cycle. We have to we have to execute measurements the whole time anyhow to detect errors. If we stop doing this for a while, errors may accumulate, right? So we want a higher rate of measurement anyhow. So in that sense, if it doesn't, lengthen, if it can mesh quite easily with having to do QEC anyhow. Is that what?
Sorry,
So
we're worried about measurement basically during the gauge.
yeah,
fixing
but the point
process.
is, okay. So let me say one comment about, maybe you've seen this. Actually, I have it on the slide. So this use of the 3D code to do the T and the gauge fixing. There was some analysis also how this fared as compared to with overhead as compared to the surface code with magic state distillation and so on. And overall, I think the answer that was by Beverland and Svora and Kubica, I think, overall the thing, you maybe know this paper, the thing was negative, but this also is very much related to the threshold of the color code, being somewhat lower. And I think these threshold estimates are in some sense very simple. Let's say if I have to do 6 C0s or 8 C0s to do, to measure a parity check, I have an error rate of 6 times the error rate of a C0. And if I have to do 4 C0s, it's 4 times C0. So it's very simple. It's very hard to get a code that has higher weight parity checks to perform very well, basically, because of that simple fact. At least with simple noise models, but then you can say, well, but I have a very specific, experimentally motivated noise model. I can do, controlled P, controlled parity operations natively with very low error rate. Then you're in a different. I went down a different direction. But I don't think this measurement that you have to do gauge fixing and extra measurement, that's not the sort of the drawback of that scheme necessarily.
Okay, thank you. That's very insightful.
Okay,
Thank you.
Yeah. At least according to my opinion, which is, yeah.
Okay.
Yeah. Hello. I have a question also.
Sorry, where is the
yeah.
speaking?
Yeah. It's about the definition of LDPC code. I'm still just a bit confused with the... so when you said that K over N is lower bounded by a constant, can you re-explain about with respect to which variable? Because I expect the larger the computation, necessarily we need more.
Okay, yeah, it's not about the computation. It's just a property of the code. First of all, there's the thing LDPC. Was that clear? So that's just a fact about parity checks, not about rate or something. And then there's this adjective good. And that traditionally, for classical codes, has been a property that the rate is constant. And so it's a code family, first of all. It's not a single code, right? And so we have codes in which code families, the rate is constant. And constant, I mean, it's like, it's at least a tenth or something like that. for all codes in the family. Right? So it's really a number. It doesn't decrease when, it doesn't go like 1 over n or something.
But well, the thing I'm confused is that which with respect to which variable we say it is constant, in the sense that
well, n, for example.
Okay. Okay. Thank you.
Okay. Well, yeah. Maybe if you have maybe I can explain the break. Yeah. Yes.
Thank you for great talk. So you're talking about polylog overhead in space and time in FTQC, and constant space overhead is possible. This is clear. And my question is, even if we use conventional protocols like surface code, concatenated 7-qubit code, I've never seen constant time overhead is achieved. So my question is, what do we need to achieve? What do you think we do need to achieve constant time overhead?
You mean this last question?
Yes.
Well, yeah, like I say, it seems hard. So,
Seemingly, yeah.
So maybe you should go for a no-go instead.
Yeah, there must be something from the...
Because the point is that the surface code does not give a constant space overhead, because there, the problem is that if I have a larger circuit or a deeper circuit with more gates, I need a higher accuracy. Therefore, I need a larger distance code, and then that translates back into a larger spatial overhead.
This also happens in time. This also happens in time.
Yeah,
My question is about time overhead.
Yeah. But so I would think more, so I'm sort of negative about this, or you need to go in. Yeah, I don't know. I haven't. Like I said, it's maybe more of a no-go direction, but I have to be, yeah. Prove a no-go. Other questions?
Hi, thanks for the nice talk. I had just a question about doing non-Clifford gates transversally. So what's the state of the art? Like, what's the best method to do that?
Yeah, so there's this, which relates to the other question, there is this, well, there are Reed-Muller codes. So, oh, no, I actually have it on the other slide, so. Sorry, just cycling through some other things. So there is a 1513 three-dimensional color code. So the three-dimensional color codes have, well, you say, well, what are your checks? Because there are cells and there are faces. So for the 2D color code, the X and the Z parity check have the same support. This is not true for the 3D code. And there are some results that if you have, you can do a transversal T gate or any gate in this C3 for a three-dimensional color code. And if you go higher for four-dimensional, you can do gates in C4 and so on. But then the point is that, and then like so she mentioned, there's a nice scheme by Bombin and all in which you can, because this thing, it doesn't have a transversal Hadamard. So you want to, but you can kind of switch between this code and a 2D color code. Like for example, this state A is T on plus, so you do that transversely, and that's like your 3D sort of, tetrahedron here. And then you have here an encoded, say, a 2D color code, and you can do a C0 between them, which sort of touches the bottom of this tetrahedron and the surface. And then you measure this, and you do an S gate here, which is again transversal. So that's a scheme that has been looked at, but the overhead. See, the point is you do need to do something 3D, and these parity checks are also higher weight, and well, there's advantages in terms of decoding, but then this trade-off is subtle. So there has been one study doing that. Let's see, here's that study, Beverland, Kubica, and Svora. But I think the bottom line there is because the overhead is sensitive to this noise threshold, right? Because if you're very close to the noise threshold, you have a lot of overhead. If you're far below, you have a little overhead. And so if the noise threshold is high, then, is low, then you're more likely to have large overhead. Yeah.
Thanks.
Yeah. But there are other schemes also, but okay, it's hard to summarize every one of them, but Oops. Okay, so we take a break then?